So please sit down so that we can start today. So today we have a foreign speaker, and I'm very happy to welcome here Dr. Massimo de Agrò from Italy, and who will be talking about the topic that is not very common in this seminar. Just very shortly, his history. So Massimo has been actually trained in psychology. First the human psychology, and then he switched to animal psychology, but not of vertebrates, but invertebrates. So his model systems include ants or spiders, basically arthropods. And he's mainly interested in the brain, or in the way how these small tiny brains, which you can find in the body of spiders or insects, actually can process a lot of information that they need for the daily life. And as you can see, and I think he can hear in his lecture, he will tell us how this information can be implemented by humans, for example, for development of more effective algorithms, and on the way around, how we can learn from them, right? So Massimo, the stage is yours, and
Thank you very
here we
much.
go.
Thank you very much. Can you all hear me without a microphone? That's fine. Great. So, yes, as Stano said, I'm a psychologist, which is quite of a weird expertise to be here talking to you about not psychology, but biology and engineering. And this is because I'm kind of a weird researcher that tries to go around a bit between topics. But I will try to put in some information about psychology so that I will not sound completely out of my mind. Rather than deciding to talk to you about my own research, mainly, I tried preparing a topic that may be of your interest and maybe of use for you. Maybe you'll come out of this lecture knowing a new tool that you may use in your own experiments in ethology, or maybe you will come out of this lecture knowing about a new job you may do as an ethologist, helping engineers do other stuff. I will throw in some of my own work around these different topics I'm going to tell you about, but I will try to inspire you and give you some tools rather than just telling you what I do. Today I will go through these 3 points. I will first start with a bit of an historical perspective of the marriage between ethology and engineering, so where it comes from, in my opinion. Then I will talk to you about some tools. Simon, just a second. Yes?
I need to finish the recording.
Fine. Sure. Shall I wait?
No, we could.
Okay. I will then move through some tools that computational neuroethology uses. This computational neuroethology is the discipline of the study of animals and the brain of animals through computational tools. So software and automation and artificial intelligence. So which tools can help ethologists understand their animals. And then we're going to do the opposite. What discoveries in animals, ethology, and the brain have brought to new innovations and discoveries in engineering, and how this can be helpful to engineers. So, let's start with a bit of an historical perspective. How many of you, raise your hand, have heard about Skinner, or have studied Skinner? I will not ask more questions. Behind people are timid or not heard about Skinner? I will tell you a bit about this scientist. I see that this is a name that has been studied and described. Bruce Skinner was a psychologist, nonetheless, in mainly the 70s in the USA. And he is one of the fathers of conditioning, and specifically he is the discoverer of operant conditioning. And operant conditioning is the process in which an animal can learn a new behavior, can produce a new behavior when this is rewarded. This is very similar to what Pavlov discovered, which is classical conditioning. But in classical conditioning, you just join a stimulus with a different stimulus. One stimulus is neutral, ringing of a bell, and one stimulus is sit by the animal, generally food, but it can be a mate, it can be a shelter, it can be the removal of a painful situation. And that's classical conditioning. In operant conditioning, rather than linking food with another stimulus, you link food with a behavior. So the animal produces a behavior, and the animal is rewarded for that. And you'll have to know Skinner is one of my favorite scientists ever. And at a conference one day, he decided that rather than giving a talk, he would actually do a full experiment on stage. The best. Which I'll now show you, if I manage to put the mouse here.
Another pigeon now, and I will try.
Is the audio good enough to understand the wordings?
And make it a more frequent part of the repertoire of the bird. Okay, fine. The bird has been already conditioned to eat from the magazine sounds and the light flashes. Now we'll just watch its behavior a bit. It's not doing anything in particular, you see. Well, I'm going to try to get it to do something. Suppose I shape up the behavior of making a complete turn. What I do is simply let it then wait for some part of that behavior. There's more of it, you see. Well, you can see the effect is instantaneous. I'm waiting for it to turn counterclockwise now. And I reinforce that movement. I wait for a more pronounced movement than that. Have to be more than that. There we go, all the way around.
I would have loved to be there. The best conference ever. So, this is operant conditioning and specifically shaping. And shaping is a process of operant conditioning in which behaviors that bring the desired behavior forward are rewarded. So you want to teach... oh, that's concerning. Okay. Behaviors that are similar to the one that you want to generate are rewarded more and more. And so you want the pigeon to turn around itself, you counterclockwise, and so you first reward a bit of a shift, and then a more pronounced shift until you get the behavior you want. Some of you may be starting to wonder, well, what does it have to do with technology and behavior? Well, this machine here is the one that has to do with technology and behavior. Skinner is the inventor of what today we call a Skinner box, which is in effect a robotic system that associates different stimuli with different events to get an experiment to fruition. And so we discovered this operant conditioning when we had a tool that was specific enough and powerful enough to actually associate the food and the behavior this precisely together. Because if you want to generate this a new behavior, and if this behavior is much more complex than the natural behavior of the animal, you need to very precisely time this reward. And so the Skinner box was born. And now you will see in this video, it's a bit cheating. It's not really a robotic system because it's Skinner that is pressing the button. But with time, he developed more complicated tools. These, we don't need the audio, these are two pigeons playing ping pong. And the reason why they're playing ping pong is because their Skinner box, the one linked to their side, you will see somebody winning eventually here. Yes. Their Skinner box is automatically linked with the falling of the ball on the other side. And so both pigeons are just trying to get the ball to the other side. And if you put them one in front of each other, then you start seeing this very complex behavior of the pigeons competing to win the food. These pigeons are not competing to win the food. These pigeons are each one trying to send the food to the other side. The more your system is complexly engineered and precise in providing the animal what it wants, the more you can generate complex behaviors and see things that you may before didn't think that that animal was capable of doing. Now, we're talking about pigeons, but we will go back now when talking about the computational neuroetology tools. I study arthropods. And arthropods have this kind of a bad reputation in psychology, but also in biology. They're like the automata animals. They're not really clever animals. They're small. They're just creatures that do automatic things. Well, you know, until now, we didn't have many Skinner box for invertebrates. And we started thinking that other animals, which were not humans, were actually capable of something more than stimulus response when we started having nice tools to understand how they work. And this is where it started. Skinner is the one that started this marriage between this engineering and the study of ethology. And Skinner was also the one that started doing the opposite. Have you heard of Project Orcon? Raise your hand if you have heard of Project Orcon. This is a delicate story because it's about war. But I think it's a very interesting one. Skinner, at some point during his career, decided that since he was capable of teaching pigeons virtually anything, he became kind of a VIP in the US, he started thinking that he could teach pigeons to drive missiles. Before the existence of, now that I say that, some of you have heard of this, maybe you didn't know it was Project Orcon, but Skinner started thinking that he could teach pigeons to drive missiles. He started thinking that you could put a pigeon inside a missile and teach a pigeon to aim for a boat, a plane, or something you need to destroy with your missile, and I'll press play. And this video has no audio, so I'll tell you about this. So what he did is he took pigeons and he mounted on them a sort of apparatus to control the movement of an object. Let me skip a bit forward. These pigeons were mounted on a holder so that they couldn't move. And first, they started teaching the behavior of pecking on an object on screen. And the pigeons are very good at it. I mean, this is a very easy behavior that you can produce. And then, you can start complicating a bit this behavior. Let me show you. And make the movement a bit more scattered and complicated to follow. And then after that, you can start teaching. You can't see very well. Let's see if I find a better angle. You can start teaching them that they really need to peck the boat, the military boat. How this system worked, you can see it here, but attached that little attachment they have on the beak, there was a string. And so the string was attached to the missile controls. And so if the pigeon pecks downward, the string gets pulled and the missile steers downward. And the multiple string pull on different controls and the missile starts going in different directions. Unfortunately, for Skinner, around the same time, rudder control missile came out, and so this project was scrapped. But this was the first idea on how to do the opposite. Okay, so now we have technologies to better understand and shape the behavior of animals. Let's try to do the opposite and use animals, which are the best machines that nature have produced, to actually aid our technology. We don't need to do everything ourselves. We can start not from scratch, but from already existing behavior. And so today I will tell you about what today is available for both these tasks. So understanding the animals and designing new robots thanks to the animals. And let's start with this field of computational neurology. As I told you, this field of computational neurology is this, the study of the behavior of animals using automated techniques. And the first techniques that I want to tell you about is the evolution or the modern cousins of the Skinner box. In a Skinner box system, your experimental aim is generally trying to understand what an animal can discriminate, or in general the learning part of the animal. Let's say I have a mouse here that is trained to push the lever when it sees a specific stimulus, and it will get food. Having this setup, I can ask many questions. For example, can a mouse see the difference between red and green? Well, a way you could do that is to show two different color lamps and say when the mouse pushes the lever on the red, it gets food, and when the mouse pushes the lever on the green, it gets electrocuted here. And the history of animal behavior is full of horrifying realities. And so you train the animal to push the lever on red and green, and if it learns that, you can say, well, it definitely can tell the difference. And if it doesn't learn that, then you can say that, well, probably it can't learn the difference. Because if it could see the difference between two stimuli, it would try to not get electrocuted and try to get food. And this is also used to study the memory of the animals, and so maybe you repeat the presentation and then you wait for a bit and you see if the animal remembers. There is an enormous amount of things you can do. Going to invertebrates, we have bees. Have you heard of proboscis extension response? Please raise your hand so I have a measure of the amount of people who have heard the proboscis extension. Proboscis extension response is a reflex that bees and bumblebees have when they get near food. It's like the drooling for the dog. The bee, rather than drooling, I'll show you a small GIF. Rather than drooling, the bee pulls out the proboscis, which is this little tongue, and it starts drinking. And this is used a lot in learning experiments. So you generally put a bee in a system in which it's blocked, like the pigeon before, and then you present different odors, for example, or different colors, or whatever you want. You show them things. And then you associate the presentation of that thing, that color or the odor, with the presentation of some sugar water. And so the bee starts licking the sugar water, and after it starts licking the sugar water, at some point it will associate the presentation of the sugar with the presentation of the color or odor. Well, this is a horrible experiment to do. I can tell you that you either need a lot of patience or a lot of students. And both of these are not very easy to come by, because what you do is you take a bee, you put it in a holder, and then you go with a little toothpick or a little Q-tip with sugar, and then you push a little pump to give some odor. It's very complicated, and if you get it wrong, the timing between the sugar and the odor, the experiment doesn't work completely. And so you may end up saying, oh, this animal can't tell the difference between these two odors, but that's not the case. It's just that you weren't good with the timing. And so using an automated system is much better. And this is what this is. This is quite new. This is an automated PER response system. This is, funny enough, called a revolver, which you put different bees in here. You can see here they have all been prepared, and you mount them here. And then you can see here in front, this is a zoomed-in version of what's happening here. There is a little feeder with the sugar that goes in front of the bee, and then this is a little nozzle for presenting an odor. And you mount the system and you press start. And the video before is a video of an AI trained to recognize when the bee is extending the proboscis. And so using a combination of, for the people among you that may be a bit of a techies and like these kind of things, with an Arduino, which is a small microcontroller that costs, I think now it's 10 euros or something. And this is a motor controller, it's another couple of euros, the motor is going to be 10. These things cost, I think, 50 euros in total, 80 euros in total. With this, it's infinite students all the way. I mean, this is 8 students' job all by one. I mean, I'm now joking, but can you see the potential here? The possibility of asking more complicated questions. Many times when we study insects and we want to say that they do something very complicated, you need to be there with them for hundreds and hundreds and thousands of trials. And this is how we got to know that parrots are clever. It's because Irene Pepperberg, the lady that started the experiments on Alex the parrot, have you heard of Alex the parrot? It was quite famous. Parrot talking and knowing concept of zero. Well, that worked because it was a house animal, spending 24/7 with the person trying to do the experiments on them. You need time to get to the core of the complication of the animal mind, or the animal brain. Having a system like this, it's a way to solve this problem. It's a way to increase the complication, the amount of data you can collect. Of course, spiders are much cooler than bees, and I'll tell you a bit about the system that we use in our lab. This is a virtual reality system for jumping spiders. You can see the spider here. What you see here in this picture is a tiny spider with a tiny magnet on its cephalothorax walking on a polystyrene ball. And since it's attached here, the spider can't move actually, because the cephalothorax is blocked on the magnet and it can't move. But it can move the legs. And moving the legs generate movement on the sphere. And this one is a computer monitor. This means that you can do stuff like this, in which you have the spider in front of the screen. Did you see the movement there? I'm not sure if you can see clearly the ball. It's a bit dark, but you can see rotations there. And then we see that things were moving on the screen. Jumping spiders are cool because they're spiders, but they are cooler because they are quite visual spiders. And so my research mostly focuses on how their visual system works, as Stano said before. And so this experiment was done to see whether they would prefer turning towards a specific stimulus or another one, depending on the characteristic of the stimulus or on the state of the animal. And that's very complicated to do without a system like this. Because if you just have a free moving animal, you can't control for orientation, perspective, distance, especially if you want to show them two different stimuli, like in this case, and see which one they prefer. If the spider is 1 centimeter this way, the experiment is to throw away. Because it maybe saw one before the other, rather than just preferring one another. Of course, this system, I'll show you now how it works. If I manage to show this. This is how the system works. So here you can see the spider as before. This is a different one, but the concept is the same. The spider is above here, attached, and the ball. And this camera, a second camera, records the ball itself. And the ball, like any 3D object, can describe by 3 axes and rotation around 3 axes, which are Z, the X, and the Y axis. And just with this signal, which is very fast to collect because it's not a lot of data, you can see exactly where the animal wanted to go. Our specific behavior that we look for is the turning that now will happen. The jumping spider, these peculiar pivots in which they shift towards an object very clearly and very rapidly. Should happen any second. Yeah, this one. So you have an animal looking at objects, a system that records all the intended movement. You're very data rich. This is done at 120 frames per second. You can create a virtual reality paradigm. In fact, lately, we are also trying... let me stop this. Or not, let's do it. We are trying to make it working on a virtual reality system. And so, rather than just being object moves, I read data from the animal, it's also the animal moves. Since the animal has moved, the world shifts with it. Exactly like a virtual reality paradigm. And this allowed us for really experiments that we couldn't do before and we couldn't understand before. And this tool that I'm now presenting you with spiders exists for Drosophilas, exists for ants. Actually, for ants it's commercially available and it's even bigger. You have these massive spheres. You have full rooms with the ant working on the sphere and being recorded by a camera. They're used to study navigation rather than just vision. Or there are a lot of use in optogenetics with Drosophilas. So, to keep in mind. But the cooler applications that I think most of you can definitely use, and I hope that you will come out of this wanting to use this in one of your experiments, is the classifiers. The tools I told you about until now have all have one big disadvantage, which is quite sad, which is that you need to build them. They're not immediate to use. You need to get the object, build the object, or buy the object. That becomes expensive. Or in general, they're more involved than any experimental procedure you can use in the lab today that you may be used to use. Classifiers are different things. I'll ask again, have you heard of classifiers? This is definitely not your topic, but maybe if you are curious about self-driving cars or artificial intelligence in general, it's today a lot in the topic talked about. Please raise your hand, let me know. So classifiers are artificial intelligence that, given a picture or a video feed, can tell what's there in the video feed. So this is a nice example of a self-driving car of undefined brand going around the street and recognizing all of the little objects that are relevant for it. And this is done with artificial neural networks which are fundamentally matrix algebra, not much more than that, but have been trained on many pictures. And so there has been a human going there and clicking on this picture on every car and this human has done this for hundreds or thousands of pictures, and then the computer ate all of these pictures and labels, and it learned the right calculation to spit out what's a car. Why do we care? Well, because things in videos are not just cars, but can be animals. And today I want to talk to you about this beautiful tool, which is DeepLabCut. DeepLabCut has been published, I think, for the first time in 2018. In 2018, and it's a system that can let you track any animal, even in the wild, using artificial intelligence, and let you study the pose of these animals. Let me check something. Yes. There are many tools like this. One other tool is YOLO or YOLACT. They are called like this because programmers are fun, and so they decided to call this tool You Only Look Once. These are all systems that, thanks to a training from a human that says, hey, I'm looking for something shaped like this, then the tool learns and spits you on a video feed the position of the animal or the area of the animal, or all this information are contained in the video, frame by frame. This, for example, is a tool using YOLACT, which is software, that is used for nematode experiment. So, nematodes are these little wormish creatures, and I'm sure you know them. They are all the craze in general biology. And before that, you would take a video of the behavior of nematodes, and you have somebody being there and saying, oh, the nematodes are doing behavior X or behavior Y, or are clumping together, or being far from each other. Instead, after having had a human take a subset of frames, 200 frames, 200 pictures, and saying in every frame which pixels corresponded to nematodes, the AI then gets trained and is capable of frame by frame tracking every nematode from thousands and hundreds of videos. Again, this is a time saver, as the tools before, but it's not only a time saver, it is also something that increases the data richness of your experiment. You can have the speed of the animals, you can have the direction of the animals, you can have frame by frame the putting together or being far away from each other. A big parenthesis on this YOLACT, but let me go back to DeepLabCut because this is my favorite. DeepLabCut also works similarly, but rather than finding where an object that you want to classify is, it works on a specific point. So you can train the AI, rather than saying, here's the Drosophila, you can say all the point of the legs, or the wings, or the proboscis, and in this mouse, all the joints in the end. This allows, not only for this experiment for the position of animals, you can easily imagine this being a colony of ants, or a general system of collective behavior. In this case, you can study the posture of the animal. You can study the orientation and these experiments of reach to grasp movement, in which you see if the animal judges the dimension of the object is going to need to grasp even before that. And you can say that by the extension of the fingers. And this system is really available for everybody today. It's been developed, but you can download it. It's completely free. You download it, you take some of your pictures, and you have this very nice graphical user interface in which you take the picture, then you click on all of the points you want the network to learn, and after you have clicked on all of the points, you let the network train, and after the network have trained, which is as easy as writing deeplabcat.train, because it's been written to actually facilitate the use. You do have this is, for example, the distance between the fingers. And you have all of this information that you can check and you can analyze on your experiment if it's relevant to you. And to this day, if you have multiple cameras, you can also track the animals in 3D. Which is, I can start to say how cool is that. The moment you start being able to track the animals in 3D, you can do even more complicated stuff on the natural behavior. Again, see that these are all nature-based pictures. They are all taken from nature. It doesn't need a lab environment. It doesn't need a white background. You just can download it, use it. For this one, even more cameras. This is not as easy. But then you end up with a level of data richness that until now it was very hard to get. Now, I don't know, all of you, what do you want to do in your life? If you have started your internship, Stano told me that you are a student of the bachelor. Master. So who started a master, an internship? Please raise your hand, let me know. Or working in the lab in general. Well, not a lot. Not a lot.
I think they don't know what you're asking for.
Oh, working in the lab. Have you not started working in the lab? Only lectures?
Me too, working in the lab, yeah.
Yeah, right. Having started to do experiments. I don't know, guys. You have to tell me.
Not everybody is doing the experiments. Sometimes they are collecting data in the field. And
Yeah, right. But that's what I meant. Started actually
exactly.
working with animals. I don't know. Like from where I'm from, generally, for the first year of master, you don't do a lot. Then you start in the second year. It was to get a grip on whether you have started doing some actual work with animals. Whatever, if you have started, you've started. If you haven't started, you haven't. And that's life.
See, well, if they haven't started by now, they will not make the course, you know. Finish
Whatever. If you've started working with animals already, I invite you to think about the very tedious process you have to do doing an experiment. And considering whether any of these technologies may be beneficial to you. And be aware that I'm presenting just a couple of examples, which are definitely not all that there is. But I would like to invite you to look around and check if somebody automated your experiment, because 9 times out of 10, it's a yes. It's just an obscure lab somewhere in the world that published an experiment and then never did it again. But the system exists, and you can definitely find it. But, that said, I want to move to the part that I find, to me, most interesting. This is what I do as a researcher, so try to understand the animals to instead aid the technology, so the other way around. And I want to talk to you a bit about what do they exist, and what I think is the role of the ethologist and the biologist in this. Because I can tell you that this field of bio-inspired robotics, it's very lacking in biologists. Generally, engineers read biology paper, they understand biology paper, and they try to replicate the system. But this is not great. I think that there would need more people that having a background in biology and ethology to actually inform a lot of the decision made during the process. Now, I will tell you, of course, about things that work. I will not tell you about things that don't work. But be aware that this field is emerging. It's it's starting, and there is a lot to be done here. So let's start talking about cyborgs. it's been quite of a mad scientist vibe for a bit in the field of engineering, in which trying to understand the working of robotics linked to brain, there is a lot of cyborg stuff, in which circuits are merged to real animals. Now, this, I have the picture here, but I'm not going to tell you about this experiment because I find it disgusting. If you want, be aware. I mean, I don't know your stance about ethics, or if you talk about ethics in animal research. Be aware that today you can buy from the UK as a kid's toy a kit for mind controlling a cockroach. It comes without the cockroach. You have to find the cockroach yourself. But it's a system like this in which you can attach to the cockroach a circuit and then control the cockroach by sending electric signal to its brain. I find it horrifying. Well, I see the research potential and interest. I find it horrifying that you can sell it to kids through Amazon. But that's life, and I will want to hear your opinion on this. I think that this is a very interesting topic that requires discussion. I will not talk about this. I've talked about this, but I will not talk more about this, and I will tell you about this instead. Because I think this is more of a midway. This is not a toy. This is an objective, but I still find it quite horrifying. But I'm less sure about my stance on this. I will just play the video.
Explosive detection. This is a real thing, and you're about to witness, step by step, how these honeybees are collected, qualified, trained, and finally transformed from mere pollen collectors into explosive detection specialists. The journey begins when the honeybees are first drafted from their hive. With the help of a specially designed handheld device, the bees are safely collected inside a chamber before being transferred to the lab. Before training starts, these honeybees need to chill. The bees are cooled to slow down their movement for handling purposes. The chilled bees are then safely placed into their harness and left for about 30 minutes to get used to their new environment. But loading each bee manually into a harness is kind of a tedious task for a technician. This is why some labs, like the Visual Communications Unit at Rothamsted Research, came up with an automated bee loading machine. The bees are confined, so they're forced to walk into a cylinder one by one. Each cylinder is then dropped into the loading tube, where each bee is slowly and safely pushed into the harness and then placed into position. The bees are typically kept in the harness for a few days before being released back to the hive. But how do you train honeybees exactly? Honeybees are amazing at detecting chemicals in the air.
I guess I'll skip the VR part. I talked to you about it.
The simple steps required to condition the dog also apply to bees. Second exposure to an explosive after receiving it. The bees are placed into a platform which is then loaded into a monitoring momentarily after receiving the explosive scent are ready for field work.
So they've trained them on the explosive odor with PR.
Visually looking at the bees, how do you exactly monitor their response? There are two ways to do this. One, with the help of a camera. The bees are placed into a platform which is then loaded into a monitoring device. The camera inside the device records the bees up close. With the help of some computer vision algorithms, the camera output can be interpreted to know when the bees purr. A unanimous purr signal from all the bees point to a high likelihood that they have detected the particular type of explosive that they were trained on. The second way of monitoring also involves a cartridge of bees being loaded into a machine. But instead of a camera, there is an infrared LED in front of each bee. the infrared light hits the bee and then bounces onto a light sensor. Based on the amount of light picked up by the sensor, it can tell if the bee had its tongue out or not. Now for the real test. 6 cartridges are loaded into a handheld detection device. Each cartridge has 6 honeybees on it. Note the infrared light in front of each bee. A monitoring screen shows 36 green squares, each representing a bee that has not yet responded. To test an air sample, the handheld detector is held in proximity to the target. And with a push of a button, all 36 bees are exposed to the air in the bag for 6 seconds. If a bee extends its tongue, the corresponding square turns from green to red. What's cool is that the bees in each cartridge could be trained on a different substance, so the device could detect not only the presence, but also the type of substance. After a few days, the bees are released back to the hive. It takes months to train a sniffer dog, but honeybees, you can train them in a few hours. The maintenance cost of bees is also a lot less than dogs, just need some sugar water. But more importantly, there are certain applications where bees may be a better fit than dogs, say for detecting landmines. It is not impossible for the weight of a dog to trigger a landmine. The African giant pouch rats are typically used for sniffing landmines, since they're effective and only weigh a couple of pounds. Even though bees can be trained to detect landmines, researchers soon realized that walking across a minefield with a handheld detector to see whether the bees stick out their tongue wasn't the best idea. So instead, they released the bees and used drones to monitor them. The trained bees tend to cluster around places where mines are buried, in the hopes of finding food. Analyzing the footage captured by the drones could reveal where landmines may be hidden in the ground. But not all animals are trained to help with detecting explosives. Some were trained to deliver them.
It's
Many are familiar
this
with the
talk.
anti-tank dogs that the Soviets trained.
It's enough. The rest part, if you're interested, maybe I can play it, the rest later. But it's less relevant to the talk. So, I mean, I don't know what you think. I would say not great. I didn't love the cartridge made of bees put in the device. But I'm sure there is different arguments about this, because in the end we do use animals to do these kind of things. And what is this that is more disturbing? Is it because they're harnessed? Is it because they're 36 rather than one dog? And we interact with the dog, we don't interact with the bees? I don't know, I leave this to a discussion later. I would really want to hear your opinion on that. What remains is that this is a bee robot. This is an occasion in which we decided that rather than making an artificial bomb sensor, because it was impossible for us, we decided to use nature sensors and link them with our automated systems to make our sensor better. As before, when I told to you about first the Skinner box system and then the artificial intelligence, I want to talk to you about what biology and especially ethologists taught engineers about designing artificial intelligence. We know that as for body plan and body characteristics, behavior can be evolved. And behavior can be evolved either mainly by changing shape in the brain. If you change the shape of the brain, you change the circuitry and you change the behavior emitted. So let's say I have an artificial intelligence. I have a self-driving car, or I have a robot dog having to go around. And today we have this problem. I'm sure all of you have played with ChatGPT at some point. None of us know how you write ChatGPT. Nobody wrote the software for ChatGPT. This is the weird state in which technology is today. You don't write the code for ChatGPT. You don't say, if the user writes X, then you write Y. There is this long training in which ChatGPT AI read hundreds and hundreds of pages on the internet, and it just predicts which is the most likely word that needs to be produced after a word before and a question and a prompt to create a meaningful text. And all of our AI classifiers all work like this. We just show them what we wanted, and they make it up. Which is a big problem, because we don't exactly know how they ended up there. And there are different ways in which we can train this artificial intelligence. Some of these ways, and the way I'm going to present to you right now, is based on the natural evolution of behavior. And it's using an algorithm that is called NEAT, because programmers are fun. This stands for Neuroevolution of Augmenting Topologies, which is a mouthful, and so they decided to call it NEAT. Let's say I have my little robot, and my little robot needs to collect all of the dust inside my room. Well, how can I tell the robot that? How can the robot learn that? I can't really go around, collect the dust, and then let the robot copy my behavior like I do with classifiers or ChatGPT. I can't. I need a lot of manpower to do that. What I could do is to take this little robot and make it go in the environment alone, randomly choosing its behavior. And so at the start, it will just do random movement. But then, I take this artificial intelligence and I give it a fitness score. A fitness score, in the sense of fitness, what we call fitness, the likelihood of surviving to the next generation. So every time it gets a speck of dust, +1 fitness. Every time it bumps on a desk, -1 fitness. Every time it, I don't know, rolls over, -100 fitness. And then I take all these robots. Of course, I do it in a simulation because I don't have infinite robots. I do all of these AIs, and they go around, and all of them behave completely randomly. But one of them, at random, maybe has a different weight on one of its neurons. And that little weight in one of these neurons make it go forward rather than backward. And by chance, that animal is going to collect, that robot is going to collect more dust. The more fitness an animal have, a robot have, the more it's likely to reproduce. And so, that net will reproduce and provide its genetic code, which in this case is the code, to its offsprings. And the offspring restart. This is called a neuroevolution of augmenting topology system. So, by understanding how evolution works, in terms of the evolution of behavior in the brain, we designed an algorithm which creates, it starts with a microscopic network. The inputs and the outputs. Let's say I have this robot, for this little Roomba robot that I've described, the input is a camera, so some pixels. And the output is the power to the motor, to the left motor, to the right motor, which can be forward or backward. These are two outputs, going from -1 to +1. So you only have this net with inputs and outputs, and for every generation, any new offspring can get a mutation on its genetic code. Can get a mutation in the genetic code in which it can get a new connection, it can remove a connection, it can add a new neuron between two connections, it evolves by growing a little brain on it. And then, based on their fitness, two of these networks get put together and create an offspring based on the different genetic code, and the offspring has characteristic of parent 1 and parent 2. And you go like this for many and many, many generations, and you get, oops, this. This is another video. I let it play a bit.
You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mario. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mario learned to beat this level, Donut Flames 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mario's brain. Let's play it again, but this time we'll look at Mario's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry.
So I'll lower a bit the volume because I want to talk to you about this. So this is just a visualization of how this topology has been built. This is the inputs. It's like a camera looking at this. I will actually mute it. This is just the inputs. It seems prepared, but I hadn't planned to highlight it while I was speaking about it. This is the inputs, so it's specifically the camera looking like this, and these are the outputs. If I had tried to prepare this, wouldn't have happened. And in the middle, you have all of these connections. In this case, the color describes the weight of the connection. If it's green, it's a positive connection. If it's red, it's a negative connection. And these are just neurons in the middle. And so, at every time point, depending on the input, you can produce a different output. And you can create quite complex behaviors. I mean, now, this is not a good example of a clever behavior because this Mario guy is just jumping forward, isn't it? But compared with the random behavior that it had at the start, in which this is one of the first random networks, in which there's only the input and one output, well, it was not great, was it? And it's this technique, this is this one random guy that just by chance was born with a mutation that let it press the right button only. But this is already better, and so this will reproduce, and the other will not. It seems, I think that this speaks to the importance of two things. First of all, it's a beautiful demonstration of the power of evolution, I believe. Because really, this is something that we wouldn't bet some animals to be able to do. And instead these are what? 1, 2 neurons. The full network had maybe 20 connections and 5 neurons. And you can do things that are insanely complex. And on the other hand, it speaks to the power that we can extract from our knowledge of biology, for our knowledge of evolution, to design machines. And now let's go back to a nice, effective network. Again, these are a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is evolving. It's gonna get to 10 or something. It's remarkable how complex your behavior can be with just a handful of neurons and with a simple process. Because this is, of course, not evolution in the real sense. This is just a mock evolution system. It only has a couple of mutations and crossing of genes, which are not even genes, are just neuron placeholders. And this is insanely complex, but works. I have another example, which is based on reinforcement learning. It's called reinforcement learning in the engineering sense, is based on operant conditioning. So let's say I have another robot, and I've tried having it evolve, but it failed. I had this robot cleaning, and this robot, unfortunately, my room had stairs, and this robot learned that going max speed forward would let it acquire maximum fitness, because you get a lot of dust like that. But then it crashes on the stairs, and it flips over. The problem is that once all of the animals have evolved to go max speed, it's very hard to de-evolve to some other behavior. Evolution lets you fall a lot in these the suboptimal niches, both in reality and in the artificial intelligence. So you find a system that works, your behavior works, and now you have a new obstacle in the environment, and you can't surpass it. Because your behavioral repertoire lets you do something that when you hit this new obstacle, you just die. And so what do animals do? Well, animals are not just machines that go straight head first in the steps. They can learn. And so they go head first in the steps, and they don't immediately die. They learn that going head first in the steps is not good. And so the next time, they change the behavior. So you don't need to necessarily change fully your brain to change the behavior. You can change the behavior online. And this is what engineers have tried to replicate using the reinforcement learning algorithm. The concept is exactly this. You have the agent, your robot, your animal, and you have the environment. And the agent knows about the environment because it has eyes, it has a camera, it has sensors, it has whatever, but also knows what it's doing. And so the agent knows that the action I made now, given what I'm seeing now, is bringing me this amount of reward or punishment. So I ran head first into the steps, I got punished. If I only had to base myself on evolution, you just collect the maximum fitness at the end. If it survived, if it reproduced, that just goes through. Instead, if you can, at every step of the way, know what's happening, you can adjust your behavior online. And this, it's something I did. This is a beautiful spider. It clearly looks like a spider. And this is a Drosophila mosquito. It clearly looks like a mosquito. And I designed a system in which I wanted to check whether a spider, given its eye positioning, would be effective as a collector robot. And so you have the spider agent, which I'm going to train with reinforcement learning. These are the posterior eyes, these are the anterolateral eyes, and this is the anterior medial eyes. And the spider exists in a world in which Drosophilas appear. And if a Drosophila appear, the artificial intelligence spider gets this information and has as an input that it's seen a Drosophila. The spider gets some reward if it eats a Drosophila, it just needs to touch it. It gets punished if it touches the wall, and after some number of frames, it dies, and so it can't eat anymore. So at every frame, at every step of the way, it will know which action it did, and if it gave it some reward. And after around 1 million of actions, this is what the spider gets to do. Of course, it's a massive approximation of what a spider is, because this is just a cube translating on the environment. But the point here is not necessarily the biological fidelity. Again, here we're not talking about saying something about the spider. Here we're talking about saying something about solving real-world problem. I mean, if this was dust, if this was an object you need to collect in some environment, you can design a robot informed by reinforcement learning that learn to collect all of the objects. Again, this started by knowing nothing about the environment. And this is even more evident. I like very much this, this viewpoint. It is not very precise in its movement. You can say it's a bit uncertain yet. But this is a very, very, very good, let's say, framework for something like self-driving cars. You place your cameras in a certain orientation based on, in our case, the orientation of the eyes in a spider. And of course, in a self-driving car, you would want to avoid objects rather than collect them. But the gist of the task is the same. You need to reach certain waypoints to go through an area. You don't need necessarily to teach the object to do the car to do that. You can give it rewards based on what you want it to do. I have another video in which there are also some obstacles, and with a bit more uncertainty, but the artificial spider can do this task without touching obstacles. You can see how you can increase the complexity of the system as many times you want, because there is always going to be, and this is a positive kind of aspect, also on this I would like your opinion, there is always a network that is going to be complex enough to solve that problem, given the reward pattern, the correct reward pattern. As it was the case for the animals in the 70s, if you have the right pattern of reward and punishment, you can teach the animals as much as you want. If you have the right pattern of reward and punishment, you can teach the robots as much as you want, following the knowledge we have as etologists. I will now move to the very last bit of the neural-inspired robotics. Maybe I will try. Maybe you will find less interesting this part rather than the others, but I will try anyway. That I like very much. Copying the brain of the animals. Until now we talked about understanding engineering. Until now we talked about using understanding of ethology to teach our robots and networks. This one instead speaks about copying the brain of animals. Not the way the brain evolved, but the brain itself of animals to teach something to our robots. And I want to give you two examples which are very famous in ethology, and maybe you'll be happy to know that they are used a lot today in robotics. So, this, it's a locust cloud flying over fields in the US. So, for us it's kind of obvious the swarming behavior, but for engineers this sends them crazy, because doing swarms of drones is very complicated because they keep hitting each other. Instead you have a swarm of locusts that absolutely never hit each other, and again it renders them crazy. How can a locust not hit each other during flight in this kind of a mess and at this kind of speed? Well, it turns out that locusts have one neuron in their brain that is responsible for not hitting each other. It's one neuron, it is only one, and it does the job alone. And it's, if you really think about it, a really, really, really dumb system. You have one neuron connected to the full lobula. The lobula in the brain of locust and in the brain of insect is the first area connected to the eye. You have all the neurons, this one neuron with all the dendrites connected to all the neurons in the lobula, If many are stimulated at the same time, you just turn, you just steer. It's easy because objects that can near you get bigger. An object that gets bigger and bigger, the nearer it is, the more pixels, the more photoreceptor is going to shade in one frame. Or in the biology sense, in one sampling rate of the eye. And so, if the amount of change becomes bigger than a certain amount, you just steer the other way. So you have two neurons, one on the left and one on the right. If this becomes too dark, you just do this. This becomes dark, you just do this. And then you keep flying it forward. And being it only one neuron, you can easily copy it into an artificial brain. And now we have drones that don't eat each other. And really, it's really that easy because it's not just, you don't need to understand that something is getting near you. It's not like this neuron fires and your main control says, oh, something is approaching, I should steer right. You can attach the axon of this neuron directly to a higher wing flapping rate on the contralateral wing. You don't need to understand. It's just an input changing the output. And so you can attach it on a robot very, very easily. And that's what these researchers have done. You just made the neuron, you attach it in this crisscross pattern with the 4 motors of the drone, and the drone avoids object just increasing the speed of a propeller. I think that many of you will know about this experiment. Today has been the lecture of horrifying tortures made to animals. But at the same time, the experiment was quite cool. This is an experiment about desert ants. We know that desert ants are very good in finding their way home. And the secret is in the name. They're quite cool because being in the desert, you don't have a lot of visual information. So you need more of an internal kind of information that you can collect. And so in this experiment, they took these ants and they let them walk away from the nest, and then they picked them up. And in the lucky one, they did them nothing. In the unlucky one, they attached little pieces of plastic from a broom to their legs. And in the even less lucky ones, they actually cut their legs. And what I observed is that the normal ant went back home in the direction where home was and actually got to home. Instead, the one with stilts went in the right direction, went to home, but then went over home and walked more. And instead, the one with stumps went in the right direction towards home, but then stopped halfway and started looking for home much nearer. And like this, they discovered that ants do have a step counter. And so the way they judge distance is in how many steps I've taken since I was home. But this wouldn't be enough, because if you just count your steps, if I do a bit of this, well, I did many more steps than if I did this. And so if I change direction many times, then I need to adjust my step count. And they do that through this system that is called path integration, in which when I go away from home, at specific time points, but probably continuously, I save up my direction and how many steps I've taken. I don't need to remember the whole path I've done, I just need to update this vector. I need one angle and one number of steps. It's just 2 information. So if I walk this way, then I know that the nest is this other way, and I know where to come back. Now I walked a bit more until here, and I just need to calculate the new angle. And so at every point, they have an angle calculated. And they discovered this by, again, taking ants, and after they went away from the nest, picking it up, putting it somewhere else, and the ant walks back, and it walks exactly in the direction where nest would have been. So it works, I've taken it, I place it here, and go straight down. This is an absolutely simple system that creates a very complex behavior. You need a count of step, an angle, and you can bring a robot home, which is another very complicated task that now can be done with a total of 3 neurons. And so now we do have land robots that just have in their brain, like the ants that have a sun compass, they have just a digital compass that can tell them where the sun is and where I've been and where to go until now. A couple of motors adjusting the direction, and using just the system, they can do homing and return home. These were some examples. There is hundreds and hundreds of other robots that are based on animals. This is Spot. I'm sure you have seen this somewhere doing PR for Boston Dynamics. I haven't talked at all about all the biomechanics that exist, all the discovering biology that help us design new robots, because I think for me it's more interesting the computation and the brain and the intelligence. But there is a lot of this, and we are only at the start of this direction, of this topic, and we really don't know what else we are going to end up discovering and having. And I hope you'll be part in some way of this technological development, and that you will find somewhere to do in this space, because I think this really needs some more biologists. With that, thank you. Please ask questions and let's discuss.
Thank you, Massimo, for a very fantastic talk and the content that you have shown us, and I think we have been inspired, and hopefully the students remain inspired. So, come on to the questions. Yes, please.
So, hello, thank you very much for a very interesting presentation. The first question I have is, if there is any other stimuli, such as, for example, food is there anything else that can be used for the driver of the animals?
As a reward?
Yes.
It's plenty. It depends on the animal, of course. As I've told you, mate is generally a big driver for a lot of animals, if not all of them. But in general, it is a very hard topic, because in the end, the stimulus you attach to the food becomes rewarding itself. So if you take a Pavlov dog and you ring the bell together with food, and then you teach the dog to do stuff, the bell itself becomes rewarding. I'm sure if you have a dog, or if you've seen a dog, you know there is this clicker, right, which makes a sound. At some point for the dog, hearing the clicking becomes a bringer of joy as much of the food itself. And so it is very hard to answer your question in the sense that you go and you see an animal, and you see that something for this animal is rewarding. Is it because it's commonly associated with a naturally rewarding occurrence? Or is it a hardwired rewarded thing itself? Mating, probably we're on the safe side and saying that it's biologically relevant in itself. As food. Shelter is hard. Because having shelter definitely lets you survive, but we don't know if animals feel reward when they find shelter because shelter itself is rewarding, or is because it's attached to the social group. For example, an ant. Is the ant happy because it found a nest, or is the ant happy because it's rewarded by being together with the other ants? We have no idea, but this is part of the interesting part of these experiments, in which you can manipulate not only the stimulus, but the reward itself, to see which of the things are effective as a reward.
Thank you. I have another question. Sure. That's okay. So all animals, all this mechanics, is just also for the humans, right? Because for us to develop technologies, to develop general like well-being of humans, do you think, is it used also for the animals themselves, for example, for conservation measures or anything in general? Because as I know, the recent studies also show that the extinction of the megafauna is because of human expansion, not because of the climate change, for example. So do you have any information if it is also used, this technology that we developed with the help of the animals, also to help them somehow?
The link is hard, the link line is harder to draw. There is a lot of technological developments that are robotics specifically, that are designed to help the environment. For example, some robots mounted on Spot are used to monitoring fauna in forests. It's a very hard task in engineering. I will not bother you with the details, but in general, having to walk around a place which is very cluttered and very unstructured is very hard for robots. It's very easy to put a car on a road because the road is a road. You just follow the road. Having a robot that have to walk in the forest, orienting becomes very complicated. And so a lot of the discoveries I told you about today are useful for that. For example, if you want to send a fleet of drones in the forest to monitor the presence of animals, you need the locust brain to do that. I would lie if I said that these are done for the animals. Generally, what happens here is that the research is done, some company wants to make money on it, and then it makes money on it, and then other people use the technology developed to help the environment and the animals. I think that putting a link this direct in what is useful for the environment and what is useful for humans, it's not only hard, but also a bit, it's obfuscating the full view, right? Because in the end, a lot of us, at least I myself, do basic research, which is generally not particularly useful for a specific task. But all the things that are today useful were once basic research that seemed unuseful. And so this is in general benefiting the environment. But if this is done on the purpose of benefiting the environment, I would say no.
Thank you very much.
Okay, I would just add to this question. First of all, thank you very much. You definitely broke my brain with this presentation. My question is a bit philosophical, let's say, but since you studied psychology, you may answer a bit of it. Because I keep thinking that it's not only that the robotics, that the robots are learning from the animals or from us, but you said that giving the right pattern of reward and punishment, then you can train, and you can see that even we humans, animals, are also trained very well. For example, social sites as Instagram, Facebook, they really press hard to give you as much reward as it's possible. For example, giving you as much endorphin by scrolling, endlessly scrolling your smartphone. So my philosophical question, because you cannot divide the training the robots from training us by robots, because, for example, with the car is trained to recognize people or traffic lights, but this was done by us showing that you are not the robot by clicking on the pictures, and now it's vice versa. So what we are trained for is my question.
So I don't think I can answer that question, but I can give some perspective on that. I don't think that anybody can answer that question because who knows? Skinner, in the 80s, wrote a book, I think it's called On Dignity and Freedom. I should have to check, but there is the title is something like that. And Skinner, working for all his life on conditioning, he also used the techniques of conditioning on his daughter, because he was convinced that humans are trainable machines, and whatever you do with your kids, it's a form of conditioning. He was convinced that every behavior of every animal can be explained by successive conditioning. You can be a loving mother or a loving father to your kid, but what you're doing is you are rewarding behaviors that you want your kid to produce, and you are punishing behaviors that your kid don't want to produce. Reward and punishment are not necessarily food or pain. It can be a loving hug, or it can be being with friends or the family. And so he wrote this book, which is fundamentally depending on your perspective, a utopic or dystopic description of society based on the engineering of rewards and punishment from the state to the people. To get to your questions, I don't think that the point is robots. I think that robots are just a tool that made very easy to do social engineering. Conscious or unconscious that is. The idea of controlling the masses with reward and punishment has been there forever. It's just that today we live in this society and we see that robots are very effective in doing that, but they're definitely not the most effective tool that ever been ever. The point of view of Skinner is that it is illusory to think that if you remove robots, in his case it was not robot, in his case was the state intervention. It is illusory to think that if you remove robots, computers, the state intervention, what you are currently seeing as exerting level of control and conditioning, if you remove that, it's an illusion to think that you have removed the conditioning. You just remove the one you saw, and there is another one that maybe is not even on purpose. Maybe it's just peer pressure. It's not like your peers want you to change your behavior, but they do condition in changing your behavior. So that was the point of view of Skinner. If you want my opinion, which I think is much less relevant to the topic, but I'll give you anyway, I do agree with the fact that we today are very much conditioned by robots, but I also think that it's not the robot's fault, and the moment you recognize which influence are things having on your own life, you can get back control. But I am a bit of a behaviorist in thinking that somebody somewhere is conditioning me with its behavior, willingly or not, and that my upbringing is at least partially the effect of my own experiences. So I don't feel like putting the blame on robots for more conditioning than before. I didn't have, when I was a kid, TikTok or Instagram, but I don't think I've escaped the conditioning from the general culture and mass culture.
Yes,
thank you.
Thank you for a very nice talk. I might have two questions, but I believe they're simple. First, if it is harder to do operant conditioning for more intelligent animals or intelligent showing more complex behavior, or if there is no correlation.
I mean, you're asking the wrong person that, because I find the classification of intelligence across animal species a bit problematic. So it's very hard for me. I think that what you generally mean is...
That's why I did a more complex behavior, because I also don't believe looking at intelligence of animals through the human lenses.
Yes, no, I see where you are trying to aim with the question. It's very hard to answer because depending on what you... I think the difficulty is what you're trying to condition, not based on the baseline level of the animal. Maybe it's harder to make your animal follow your experiment because you have other stuff to do. But once you convince the animal to follow the reward pattern, you're set. There is a beautiful group in Japan, the professor is called Matsuzawa. They have this chimpanzee heaven. There's this massive environment with an artificial forest, and in the very middle there is a booth with a touch screen, and the monkeys can go there and do experiment at their own volition. So they just go there when they want treats. So they are fed normally, but then when they want treats, they go there and play the different games on touch screen. And they do that very well. And on this perspective, chimps should be the most complicated to train. But they are very hard to train if you try to force them to do the experiment. But as soon as you leave them free, they treat that as a game. And so they are very easily trained like that. So I am not sure I answered your question, but it is the best I can do, I think.
I think you did, or at least it is with my experience with trying to condition animals. And second, it may be more technical, and I hope it's simple, but I simply never had anyone to ask. Because 10 years ago, everybody was talking, I have some techie friends, about neural networks. And since we have generative artificial intelligence, everybody is talking about artificial intelligence using neural networks. So what's the difference between neural network and artificial intelligence, or is it just change of vocabulary?
Artificial intelligence is a general term to describe any artificial system that takes decisions or generates a response. Neural networks are, which technically they should be called artificial neural networks, because also the brain is a neural network. Artificial neural networks are a specific type of computational tool to make AIs. So a neural network is fundamentally, I'm not sure. This is a neural network. It's a very simple neural network. Neural networks are systems of nodes and connections. They are generally described like this, but in the end, the calculation is matrix algebra. Each of these connections has a weight and a bias. If you have done stats, it's like the intercept and the angular coefficient. To get the number that ends up here, you take the number that's here, you multiply it by a weight, and then you add a bias. Again, it's like the linear regression. You multiply it by an inclination, and then you add a bias. And then you get the number that's here. And then you go to the next layer. I mean, in this case, that's here, then you go to the next layer, and the next layer. To do that, mathematically, you can do that with matrix algebra, but this is a neural network. A neural network is a connection of nodes and weights and biases that gets to an output. Your input can be a picture, which is just a matrix made of many numbers, and your output can be dog, cat, snake, so a class. And the class is between 1 and 0, and so it's the probability of being that. So neural networks are just a type of artificial intelligence that work in this node-based way. Generative language AI is a neural network. It works the same. It still has this structure. Most of the things that you see today are neural networks. They're all built like this. Most. I mean, not all, of course. It's never everything, but it's most of it is all structured this way.
So, another question? Yes?
So once you change the behavior of animals and you stop using them, for example, for the bees, they say they release them to the hive. So do they unlearn what they learned, or does it stay permanently? Like, are they still working like any other bees?
So the short answer is nobody knows. The long answer is generally when behaviors are stopped being reinforced, they go through a process that's called extinction. So you learn something, but then it's not rewarded anymore until you don't produce the response anymore, and it's unlearned. And it's the same for us, it's the same for humans. Nobody checked how long the bees keep remembering the smell of bombs and try to go on bombs to find food. It is a similar problem we have with our spiders, that we train on the ball and then we release outside and we never see them again. And we do, sometimes we see them again, but we don't know how are they doing. It is kind of, we never have the perfect information, is what I'm trying to say. When you do this kind of experiment, I believe you have to work on educated guesses until some point, especially when you work with ethics. Is it okay to release back the bees to the hive? Would it be better to kill them because maybe they come to the hive and then they create, destroy the colony because they keep trying on bombs and then they don't eat any, they don't forage anymore, but they eat? Or is it better to release back, hoping that they will learn back to do proper bee job? Nobody knows. We can do our best in trying to do the least harm possible.
Yes, thank you very much for the presentation. It was very exciting. I have two questions.
Okay.
First is the question and the proposition. I wanted to touch the ethics of experimenting on bees and ants and jumping spiders.
Mm-hmm.
Because in all of these experiments, the tasks were really simple and primitive. But these animals are extremely smart, intelligent, and social. So why won't we, instead of using bees, we could use some insects that are generally known to be dumber or simpler or not social, or maybe the ones that harm us, ticks. We can use ticks. Everyone will be, I think, glad to do that. Or mosquitoes.
So, the reason why we know today that bees are highly social and complex and intelligent is because people have started doing this stuff when everybody thought that they were dumb and unuseful and stupid. The reason why we have this bias, that when an experiment comes out saying that an animal is quite clever, it starts getting inside us. When we don't hear about an animal being intelligent, we think it's dumb. Now, we know about this because we studied them. Then there is the other part in which there is animals we hate and that harm us and that we could study. The point is, I guess, the objective of the experiment. I don't think that animals are interchangeable depending on the experiment you want to do. If you want to study smell, maybe ticks would be okay. Although they're very specialized. Maybe you wouldn't be able to teach them many different smells. Or maybe mosquitoes are fine. The reason why these things are done on bees is practicality. Since we studied them until the 70s, now we have all these techniques that work very well, and so we have them and we use them. Is that good? Is that bad? I don't know. Honestly, I feel that from an ethical standpoint, using animals that actively harm us is not more or less ethical than using bees. At least in my opinion. I mean, we could disagree. And I recognize that if I go around and I say, hey, I have a new tool and I can exterminate all of the mosquitoes on Earth, I'm sure that most of the people will be happy with me. If I go around and I say I developed a new tool that destroys all of the bees on Earth, I will get lynched. But, you know, I don't think that from the point of view of the bee or of the mosquito, it changes a lot. It's just our perspective in which we love some and we hate some, and we decide that some are worthy of living or not. Are mosquitoes worthy of living? Well, they definitely kill humans in some sense, but I'm not sure that's kind of a slippery slope to go on if you want to decide our ethics on nuisance or harmfulness to humans. because that's what brought us here. It's kind of the reasoning of, well, it is true that polluting kills the environment, but what are we going to do? Are we going to freeze to death? No, but I know I'm speaking for absurds, but it's kind of the same reasoning, right? You have this, you have to hold both those in your mind and try to move across them.
It makes a lot of sense. Thank you. The second.
May I ask somebody else, and then maybe if we have time, we can continue. So
I'll be here anyway. So.
Yeah, this one is a follow-up actually. I'm thinking I will change the perspective. What is the intelligence? And is it more harmful to do something on stuff that you think is intelligent, or on something that can feel the pain? And do intelligent creatures feel the more pain than? I mean, what's the ethical reason to do experiment or not to do experiments on something living? So that's and mostly we don't like to see if you punish something purposely. If I step on a chicken here, smash it to a block, you will see me as a lunatic, probably a sadist, going to the KFC. No problem, right? Even to buying those chickens that are turning, you see those were chicken, no problem. Everybody can do it. So, yeah. So I mean, that's probably the problem. Why people are thinking, oh, with the bees, that's something, fishy here. Maybe they can feel the pain, but not seeing it, it's okay. So, I mean,
I see what you
about
mean.
the, intelligent relation between intelligence and suffering, and doing experiment on something.
I mean, the question is very deep, and we could talk about this for
and you were poking the discussion about it.
I know, because it's kind of, I know, I did it on purpose.
Bring it up.
I'll split it. I'll split the answer in two pieces. First of all, let's talk about the difference between smashing a chicken and eating a chicken.
Nice.
There is in the way we look at ethics today, and I'm not gonna say if it's correct or wrong, but this is a distinction that it's made. There is a moral weight to the reason why one do things. And so, being a sadist, killing an animal for the joy of killing the animal is much more frowned upon than killing an animal for the need to survive. We can stay here and argue for ages if you really need chickens to survive or not, or specifically the KFC chicken to survive. But in that case, you are enjoying the food and killing is a byproduct. If you go around and smash a chicken with your foot, the pleasure is the killing. And I think that there should be some difference in ethics in that. And also in research, and this is why European law, but also the general agreement, is that the suffering caused by a research is acceptable depending on the perceived advancement that the research can bring. And so it is always a balancing of benefit in regarding to the pain caused. And so the worst part of it is killing an animal because because I want to kill an animal. And that is very frowned upon. And the most noble part is all my family is dying, and if I don't kill this chicken, we're all gonna die, and I need to feed my baby of 2 years old. So there is, I think that there is a big difference between sadism and killing for food and killing in research. Going to the other question about the difference in intelligence, that is a reasoning that I generally try to avoid in general. Because I don't think we are equipped to state which animals feel pain and which animals feel not. Because we can only say that definitely the animal that has been tested can feel pain because we checked it and we see that and we know that. For all the ones that we don't know, we can't demonstrate negatives. And being unable to demonstrate negatives and being a researcher in this part so behind, I don't feel comfortable in saying I can hurt an ant and I can't hurt a chicken. Because the strength of the evidence is, I don't think, there to exclude without a reason of a doubt that the ants don't feel pain. There are some research that claim that ants don't feel pain. They are quite old. They have never been replicated, and instead, I think that the basic assumption that everything that has a brain can feel pain, it's much stronger than the basic assumption that you need to demonstrate that something feels pain before being able to say that. But I know that this is controversial in research, and in fact, in Europe, you can do whatever you want to invertebrates, and you don't have to ask to anybody. But in my opinion, the baseline feeling for me, the baseline expectation should be for me that everything, until proven otherwise, can feel pain. And if proven otherwise, then we can discuss.
Thank you. There is time for last questions, so Naomi.
Thank you very much for an amazing presentation. So my question is about, you have shown that if knowing about the mechanism of one single neurons can be implemented to the robot system and so on, depending on whatever we are looking for. And what about learning the neural mechanisms of, for example, which is responsible for the feeling empathy or other emotional stage, transformation and so on, and implementing to the robot? You may ask why we need a robot who feels empathy to us or to other living system, but just imagine in a life that I think we are getting out to that life, that some human life, like a homomorph robots, are working with us, even in academic environment or maybe in restaurants and so on. And probably we would be interested that those robots may feel a basic empathy or some emotions to us. Is it possible?
I think that the question about empathy and the question about emotions are, at least in some way, separate. Because we do call empathy an emotion, but what we're talking about specifically is the effect of the emotion rather than the emotion itself. If I have a robot feeling empathy, or a robot acting as if it was empathic, means putting in place some behaviors that are consistent with wanting the best for the human actor. What the robot feels inside itself, it's a different story. I mean, I've presented you a robot that has been trained with reward and punishment. Is the computer feeling joy when it touches a fake Drosophila and feeling sad when it touches an obstacle? I mean, you laugh, but because it seems obvious to us that we do feel stuff, and it seems absurd that things that are not us can feel stuff. But if you think about it, the pain, it is something that evolved in our brain to tell us what not to do, and pleasure is the sensation that has evolved in our brain to tell us what to do. So, is the robot feeling joy and pain? It's not an easy question. The question is the robot conscious at that point? Is there something in the computer that is subjectively and individually experiencing the reactions that it's getting? And it is a question for the animals. I would like to point out that in the medieval time it was a question for women. Do women have a soul? Or are they just... You know, I'm saying that because it's very easy to go there and say that somebody that is different from us doesn't have the characteristic that makes us human. When we discovered the US, we decided that Native Americans didn't have a soul. And then at some point we decided that babies don't have a soul. The soul gets there at 3 years old. And that's why you can do open surgery on babies because they don't feel pain. It's very easy when you don't see somebody emitting the things that you feel in the same way as you emit them to exclude the possibility that they have it. Do I think that the robot is feeling pain and joy? No. But I don't want to go there and exclude it a priori because the behavioral evidence and the brain structure is there to have reward and punishment. The question becomes, what is in ourselves that feels that? So to finish answering the question, can you program empathy in a computer? Super easy. You just program it to have a reward once your human smiles. Okay. That's a mirror neuron. Is the robot feeling joy? I don't know.
Okay, thank you much.